All right. So we had said that what happens is in these cardiac muscle cells, we have sort of, if you compare this to nerve function, because there's a lot of similarity to this. If you compare it to nerve function, what did we say was resting membrane potential? We had said it's minus 70, right? And then we had said something happened, action potential happened when you got to the threshold of minus 55. Well, it ends up in the muscle, something very similar happens. You start out before the heartbeat is generated, the cardiocytes in the SA node are at minus 60 millivolts, and they gradually move towards their threshold of minus 40, and that's when they start to contract. And so it's very similar to what goes on in a nerve, but the values are just a little bit different. All right, so we had said, what is this going to do? It's going to happen about 80 beats per minute. But we know if we're on that treadmill, our heart is beating a lot faster, right? And the reason it is beating faster is because of your autonomic nervous system. Remember, the sympathetic impulses are going to increase your heart rate. And the reason they're doing this is because you're working. You're working hard and you need more blood because you're using more oxygen. So you're working hard, so sympathetic impulses will increase your heart rate. Your heart rate will increase up to about 230 beats per minute. And then when you're really relaxed and the opposite situation is going on, your heart doesn't need to be beating like crazy if you're just sitting on the couch, right? So parasympathetic impulses can slow it down to as low as 20 beats per second. So even though the heart generates its own heart rate, it can be modified. It can be modified by the autonomic nervous system. All right, so we have our picture up here that we've seen before with the SA node and the AV node. Now, you may have heard of people who have problems with arrhythmias. And most of these, and it's very common for people when they get older. It's a very large percentage of people who are older have some kind of arrhythmia problems. And what happens is you get what we call an eptopic focus. And what it is it's a location in the heart that says, why does the SA node get to have all the fun? We want to control the heartbeat also. And so you get a ectopic focus, oftentimes over here, associated with where the pulmonary veins bring blood bring to the left atrium. That's where they usually are. And so what will happen is you've got the SA node periodically causing a contraction, and then you have this other location completely unsynchronized with the SA node, and it's doing it too. And so it's also generating ectopic. Let me spell correctly, ectopic. So you have this ectopic focus, which is competing with the SA node. And so if you have that going on, what's happening? We said we have the AV node, thank God, that's acting as a brake, keeping your ventricles from being stimulated to beat like crazy. But you'll end up having the atria contracting a lot. And this is what we call atrial fibrillation. And this is a relatively common problem due to an ectopic focus. Now, the ectopic focuses are not only limited to the atria. You can get them in the ventricles as well. And so when we talk about the ectopic focuses in the atrium, they will result in something called an atrial flutter or fibrillation. When we get them in the ventricle, where the ventricle just randomly contracts on its own, we call it a preventricular contraction, a PVC. And that would be when you have an ectopic focus down here somewhere. And this would result in a PVC, a preventricular contraction. And that would just be a random heartbeat of the ventricles, just completely out of sync with the contractions of the two atria. So we have a bunch of videos on here. Some of them I know aren't still functional, but make sure you look at the videos that are on this page here, which is dealing with the heartbeat and the controls on the heartbeat. I think I've talked about everything there. Where are we time-wise? Okay, we're good. I'm going to go to slide 19 here. And so why, the question is, why do we go through all of that trouble of hooking all those electrodes up on you and doing an ECG? Yeah, you can see the P wave and the QRS and the T wave, but what's the point? Why do we do it? And the reason for it is damage, right? So if you get damage to your heart, what do you think is going to happen to the various parts of that of the ECG? You know, you have the P wave, the QRS, and the T. And so what an cardiologist does is they look at that time. We said that we have time across the bottom. And we had said there's sort of normals. There's normals, time intervals that are in there. And you can look and you can see stuff. Now, if we were talking about atrial flutter, you'd get a lot of waves there before, representing something similar, what you would think of as the P wave. They call them, I think, F waves. But anyway, it's because they're abnormal. But they're representing the contraction of the atria. So you can see that on an ECG. And you can also look and see if the heart's sluggish. So when the heart is contracting, the ventricles are contracting, maybe they're not contracting as rapidly as they should. Now, what might that represent? It might represent a heart attack. That's what. So what they're looking at is the time. Time is really important in this. So if we look at what I've got on the board here on slide number 19, we're on slide number 19, you can see P, QRS. Whoa, look how wide that is. And then you don't even have a T wave in there. So you don't even see a T wave. All you see is a P and a QRS, and then we go back to another P. So this is the kind of thing they're looking for on your ECG. So we had talked about, so that's why cardiologists do this. And one of those videos is a real dry kind of video. It's like from a medical school where there's this cardiologist who's droning on, but he's got good information. That's why I have it on there, where he's talking about the timing. And they can calculate heart rates and all kinds of stuff because they have this time associated with this thing. So when your heart beats, we've talked about the autonomic nervous system, and we had said with the autonomic nervous system and the heartbeat, you can, if you increase, sympathetic impulses, increase the rate of heartbeat and the amount of blood that is pumped. So that it would be what we call the stroke volume. It's up here. It's up here behind me, stroke volume. And so when your heart is beating rapidly, it's not only beating more rapidly, it's pumping more blood. So you have this stroke volume, which is going to be represented by the amount of blood that is pumped with each heartbeat. And so we have you have the Frank-Starling law. We have the Frank-Starling law. Somebody got a law named after them. And what it basically states is that the amount of tension, remember we said the preload? So we had said the ventricle starts to contract and before it pumps blood. And so the amount of preload before it overcomes afterload, the pressure in the arteries, the amount of preload is a predictor of the amount of blood that will be pumped, the stroke volume. So it basically says is that the stroke volume is proportional to the end diastolic volume. That's the preload, the amount of blood that is down in the ventricles, which is what produces the preload pressure. And so it's all related to how much is the heart stretched. Okay, and so we have some other terms. We have the preload, it's the amount of tension in the ventricle muscle before contraction. We have contractility, of course. That's the ability of the heart to contract. And then we have this afterload, which we had said it's the pressure in the arteries and the pulmonary trunk. These are the two arteries that are being pumped into. Just distal, just on the other side of the semilunar valves. And this would be what we would call cardiac resistance. I've got 2 more slides. We've gone 13 minutes. I'm going to come back and we'll talk about